All right, well, welcome everyone. I am JJ. Let's jump in and work an example problem. So in this one, we have a pin connected truss is support as shown. A pin at A, a roller over here at B. The truss is used to support a 100 kilogram mass here at M. Let's find our support reactions. That pin connected statement, that will matter down the road when we actually look at how do we solve out what's going on in every individual piece of our truss. For right now, though, we could have taken that off and just said, find the support reactions. That's really all we're doing. So again, we're going to start out and tackle a free body diagram. We got to have a free body diagram for making equilibrium equations. So that should be our first step. For doing that, let's start by circling around our object, cutting it off of the wall that's holding it up, or the ground. Any weight that's hanging off of something, we'll snip that rope as well and go from there. But so we need to cut we'll cut the mass's cable. We'll come up and around and cut through the roller. And then we can close out that circle. And I should probably make that not look like I'm cutting the truss up here. It still kind of does. Third time's the charm here. Coming up and around. So everything inside that, our forces, are going to get included in here. The things we cut, our pin, our cable, our roller, need to show up as unknowns in our free body diagram. For us to do that, though, we cut this weight, or this mass. It's 100 kilograms. Let's convert that into a force, not a mass. We always sum up forces, never masses. So our weight that we're working with here should really be weight is our mass, 100, times gravity, 9.81. Or this is not 100 kilograms that we want to use in our equations. I want to use 981 newtons is the weight that I'm putting in here. From there, let's go ahead and get our free body diagram drawn. So our FBD. We have our truss, kind of looks like this. Something like that. It's probably a bad drawing, but we can work with this. It's not going to be at all to scale. That's okay. If our drawing isn't perfect, don't stress out about it. We did not go into engineering because we're great at art. We went in because we're smart, intelligent people. So let's tackle A. At A, I have a pin. So I'm going to put in an AY, and an AX. As I go across this, both of my sections in here, despite what they look like, are really 3 meters wide. Both of them. Again, not to scale is okay. I'm going up it to this point vertically to where the weight was hanging. That's 2 meters. And then it's 2 meters to get to the very top. At the very top of this, I have my roller at B. Roller should have one force perpendicular to whatever they're rolling on. That wall is what it's rolling against. Perpendicular to vertical gets me a horizontal force. Because it's horizontal, let's go ahead and call it BX. If that wall was inclined at all, and my force here was at an angle as a result, don't call that BX or BY, call it like an FB. Only use BX if it's entirely in the X, only use a Y if it's entirely in the Y. But the top left corner, 4 meters to the left of B, we should have a force going down. That's 800 newtons. 800 newtons. And one going to the right, 700 newtons. 700 newtons. The last thing I need, I cut that cable. Let's come in and put a force in here for our weight. Coming straight down, because gravity pulls straight down. I have the weight, 981 newtons. 981 newtons. And that should be my entire free body diagram. I have 3 unknowns, AX, AY, BX. I can apply 3 equilibrium equations and find all of them. 3 equations, 3 unknowns. We can tackle that. So we got through our free body diagram. Our second step is then just, let's tackle equilibrium. Equilibrium. We can sum forces and moments. Or we can sum moments twice and only do forces once. Or if we really want to go crazy, we can sum moments 3 times and not do forces at all. When we do trusses, and look at actual members in it. Sometimes summing moments is really useful for us. For right now, we're probably just going to do forces twice, though. If I come in here, if I sum forces in the x, I have ax and bx, two unknowns. Don't start there. In the y, I only have ay. That'd be a pretty good place for me to start at. Or I could come in some moments today. I get rid of ax and ay. Bx would be my only unknown. That's also a pretty good place for me to start. If at all possible, do one equation, one unknown to get going on everything. It's going to save us hassle. Don't make a system of equations to solve these problems unless you absolutely have to. Let's do moments first. So I'm going to come in and say with positive, going counterclockwise, I'm summing up my moments about point A. Get that equation documentation step in here. What am I actually doing? What's my equation? Then I'll set this equal to anything causing moment. I know bx will cause moment. It's going to be, if it pushes to the left here, it will cause a counterclockwise rotation about A, and it's 4 meters above A. So 4 bx. The weight here will cause a clockwise rotation, so I'm going to subtract its moment out, minus force 981 times my distance, 3. My 800 is going to cause a clockwise rotation, so I'll subtract it out, minus my force is 800, and my distance here should be, well, I don't know this distance from A to 800, but I know from A to B is 3 meters or 6 meters horizontally. From B back to 800 is 4 meters. So the difference in there, 6 minus 4, or just 2, is my perpendicular distance. We really have that distance, it's just not directly given to us. And then our last force, 700 newtons, would also cause a clockwise rotation. So I'm going to say minus force is 700 times, I need a vertical distance because it's an x force, 2 plus 2 times 4. And that's everything causing moment at A. So I'll set my equation equal to 0. In here, bx is my only unknown. I can solve for bx then. And I should get that bx is equal to 1835.75 newtons. That equation, when I worked it out, will give me a positive answer for bx. In my answer statement, I want to get the magnitude, that's what I have right here, but also the direction. Because I get a positive number out, it means I assume the correct direction in my free body diagram. This is to the left, which is another answer for us. From here, let's go to summing forces in the y. I could have done this one first. I just arbitrarily chose not to. There would have been nothing wrong with doing it first. But I have ay, I assumed went up, so put it as positive. I have 800 coming down, minus 800. And I have the weight coming straight down, minus 981. Is going to get us to 0, equals 0. Or ay is equal to, again, we get a positive out here, so I'm going to get that this is the correct direction. Ay is 1,781 newtons, and it's going up in the direction we assumed, because this solves to be a positive answer. The very last one we have is ax left. I could do this two different ways. I could solve this problem by summing forces once and moments twice. I could sum moments, really, I could do moments at B, for example, and find ax. Or I could take the easy approach and say, let's just sum forces in the x. It'll give me the same answer either way, but do the one that's going to make you most successful. What's the easiest amount of work for us? Summing force in the x would be that one for us. So I would have ax goes to the right, plus 700, minus bx, which we got bx was the first thing we found, minus 1835.75 equals 0. Ax is our only unknown here. I should be able to solve for ax pretty straightforward. I'm going to get that ax is a positive 1,135.75 0.75. In newtons, I get a positive number from this equation, which means I guessed the right direction in my free body diagram. It is to the right, which would be my final answer for everything here. I know I've said this in other videos, but rigid body equilibrium is like key statics, summing force in the x, y, and moments. If you ask a lot of engineers, what do you learn in statics? That's probably the answer they're going to give you. Make sure you can do these ones. I could guarantee you're going to see this on exams. My exam that I'm going to give at the end of this unit basically is rigid body equilibrium, and then a couple of unique applications of rigid body equilibrium. Make sure we can do this, or statics is going to be a struggle from here out. But we have a handful of videos up. Watch them. Dig into this. You can do it. I have faith in you. If this was useful for you, hit that like and subscribe button. Stick around. Let's get you an A with JJ.